Hello guys, in this video I'm going to speak about SDS PAGE, sodium dodecyl sulfate polyacrylamide gel electrophoresis. So I'll speak about several points. First, what is SDS PAGE, the sample preparation, the discontinuous gel system, and the separation principle. So at the end of this video, you will get a very good idea about SDS PAGE. You will understand everything about the principle and the technique. So I'll start first talking about what is SDS PAGE. SDS PAGE is an electrophoresis technique. It's used for protein separation. And the gel used for SDS is polyacrylamide gel. Acrylamide is an inert material, so it doesn't interact with the proteins, which is a good feature, and it forms a matrix. The pore size of the matrix can be determined by the concentration of the polyacrylamide gel, so it's a good gel. The SDS gel is composed of two layers of the gel. The first is the stacking gel. The second is the separating gel. In the stacking gel, we have the wells in which we apply the protein samples, like here. And then we apply an electrical field to the gel, going from negative on the top to positive on the bottom. The electrical field is applied by a battery. And when the electrical field is applied, the proteins start to migrate from negative to positive, and they are separated in the separating gel according to their, like this, according to their molecular weight. This is the general description, but I'm going to speak about everything in details. First of all, to understand the principle of the SDS PAGE, we should speak about the sample preparation. In the sample, we have the proteins, and we also have what we call the denaturation buffer, or the sample buffer, or the Lamley buffer, which is composed of several substances or materials. And the most important two materials of this is SDS and the beta-mercaptoethanol. So I'm going to speak about them first. SDS is an anionic detergent. It has a polar side and a non-polar side, a polar side and a non-polar side. When SDS is dissolved, it gives a negative ions, and these SDS ions bind to the proteins on the side chain of the amino acids that in the protein. So SDS gives the protein a negative charge. Whatever is the original charge of the protein, even if the protein is originally negative or positive or neutral, the SDS gives the protein negative charge. The SDS also denaturates the protein, so it converts the protein from its tertiary and secondary structure to its primary structure by breaking the bonds that are implicated in the formation of the tertiary and secondary structure. Similarly, beta-mercaptoethanol also has a role in the denaturation of the protein. It's a reducing agent. It reduces the disulfide bond in the protein, so it separates the subunits of a certain protein. So this is the protein, this is the amino acid or the peptide chain of the protein, and then the secondary and tertiary and quaternary structures are formed by non-covalent bonds like the ionic bond, the hydrophobic interaction like van der Waals bonds, the hydrogen bonds, and the disulfide linkage. And these bonds are broken by the SDS and the beta-mercaptoethanol. At the end, we will have the protein as a peptide chain. So the shape of the protein doesn't play a role in the SDS, and also the charge of the protein. So neither the shape nor the charge of the protein plays a role in the SDS PAGE, only the molecular weight of the protein. So this is SDS and beta-mercaptoethanol. We also have the tris hydrochloride, which is a buffer that is of pH 6.8. It also gives the chloride ions. The chloride ions are also important in the mechanism of SDS. I'm going to speak about them. Bromoethanol blue is a staining dye. It's used to give the sample a blue color, so we can detect the sample on the gel, the level of the sample on the gel. Glycerol increases slightly the viscosity of the sample. And also we use distilled water to continue the volume, and we use distilled water because we don't need ions in the sample. Now I'm going to speak about the discontinuous gel system. So we have two layers of the gel, as I said previously, the stacking gel and the separating gel. And they have different pH. So the stacking gel has a pH of 6.8. The separating gel has a pH of 8.8. We also have the two electrodes that have pH of 8.3. There is something called the migration buffer, and the migration buffer contains tris and glycine. Glycine is also very important in SDS page, so I'm going to speak about glycine. Glycine is an amino acid, and it's the simplest amino acid because the side chain is only a hydrogen, and it's a zwitterion. What does that mean? It means that in acidic pH, so below 2.3, this amino acid is protonated, so it's positively charged. And in basic pH, over 9.6, it's negatively charged because it's deprotonated. Between these two values, which we call pKa1 and pKa2, this amino acid is neutral. And it's totally and exactly neutral in the very middle point between pKa1 and pKa2. So how can we know it? We take the 2.3 plus 9.6 divided by 2. So we get the value of 5.95, which we call the isoelectric point. In the isoelectric point, the molecule is exactly neutral. Above this point, so at pH, let's say pH 6 or pH 6.5, the proteins start to be slightly negative, and the negativity of the protein increases gradually between 5.95 and 9.6. So we should know that in this area it's slightly negative, and the negativity increases. So let's see. When the pH is in the electrode, the pH is 8.3, and then glycine is negatively charged. As you see here, glycine here at 8.3 is negatively charged. So the glycine will migrate from the negative towards the positive pole because it's negatively charged. But when it enters the stacking gel, in which the pH is 6.8, the negativity of the glycine decreases, and then the mobility of the glycine becomes so slow. So I will speak about each one of these separately. So let's first take the stacking gel. In the stacking gel, the pH is 6.8, and here we have the sample. So in the sample, we have chloride ions. As I told you, we have the tris hydrochloride, which gives chloride ions. We have the protein SDS complex, which is negative. Chloride is also negative. And we have the glycine, which is at pH 6.8, neutral to slightly negative. So they migrate in this order. So first we have the chloride, then we have the protein, then the slowest is the glycine. So as you see here, the proteins are stacked between the chloride and the glycine. And because of this, we call this the stacking gel, because the proteins are stacked between these two. And when the three molecules reach this line, they start the separating gel. In the separating gel, the pH is 8.8. This is the separating gel, and the pH is 8.8. So the migration takes place in this order. So first we have the chloride, which migrates so fast toward the positive charge. Then we have the glycine, because when the pH is 8.8, the glycine is much more negative, and so it becomes faster than the proteins. And then we have the proteins. So you see here the proteins are left free behind. So the proteins are free behind, there is nothing, and then they are separated freely in the gel. The question is, why do we have this discontinuous gel system? And the answer is, when we apply the sample in the well, the sample is about 3 or 5 millimeters. And then the proteins will not be applied to the gel at the same time. So if the separating gel starts from here, the proteins will be applied to the gel not at the same time. But when the proteins are in the stacking gel, they are stacked together, and then they enter to the separating gel at the same time. And they are separated to give the bands, especially like when proteins have the same molecular weight, they should migrate together at the same time to give this band. Now the separation takes place because this gel is a matrix, as I said before. So you can imagine it like this. This is the polyacrylamide matrix. This is the sample. So the sample migrates from negative to positive. And when it starts in the separating gel, the large proteins cannot migrate farther because they stick in the gel earlier. I should say that the stacking gel is a very low concentration of polyacrylamide, and because of this, the proteins do not stick in the stacking gel because it's so diluted. It's not concentrated, so the pore size is so big. But in the separating gel, the separating gel is more concentrated, and so the proteins will stick at a certain point. So the larger proteins stick earlier, but the smaller proteins migrate and stick later. And then we will get different bands of different sizes of the proteins. This was everything I wanted to tell you about SDS page. I hope you enjoyed this video and you benefit from it. If you have any questions, you can leave your question in the comments. I will answer you. And if you like this video, please like and share and subscribe my channel. See you in the next video. Bye bye.